Hello, my name is Harrison Harris, and today I will be covering 9.2 slope fields and Euler's method. So what is a slope field? A slope field is a graph full of line segments that represent the slopes of a function at a given point. So suppose we are asked to sketch a graph of the solution of the initial value problem y prime equals x plus y at y0 equals 1 and y negative 4 equals 1. Now we don't know the formula for the solution, so how can we possibly sketch this graph? Let's think about what the differential equation means. The equation y prime equals x plus y tells us that the slope at any point xy on the graph is equal to the sum of the x and y coordinates of the point. Now let's look at this graph that I drew here. As you can see, it has a bunch of red line segments. Now what do these mean? Those represent slopes at each x and y coordinate. So I literally went to each x and y coordinate and drew inputted each into this differential equation and drew the line segment that represented that answer. So, for example, if I wanted to find the slope at x equals 4, y equals 0, all I have to do is, given the differential equation, 4 plus 0, then go to the x and y coordinate 4, 0, and draw a line segment that represents that slope. Now, it doesn't have to be exact, but it does have to be comparatively different to its neighboring line segments, given that the differential equation allows it. So if they're the same, draw the line segment like they're the same, but make it different so you can see the art. Now, it asks you to draw a function through 0, 1 and negative 4, 1. So all you have to do is you go to the x and y coordinates, 0, 1, and you follow the line segments. You connect the line segments to the extremes of the graph that you are given or you have drawn yourself. Similar with negative 4, 1, or not similar, exactly the same. You go to the negative 4, 1, you find that line segment. As you can see, it says that line segment indicates the slope at negative 4, 1. And you follow it, you connect those line segments, and voila, you have your graph. Now, there are some hints that you can get or extract from a slope field. So some problems are going to be like 4 slope fields and 4 differential equations, and they want you to match them. So there are going to be like 1 or 2 slope fields that are going to look like either this one or this one, and it's going to make it a lot easier for you to match the slope fields to the differential equations if you identify these patterns. Now if we look at this one, as you can see, these line segments look exactly the same if you go from the left to the right. That means that the different x values do not change the slope, and that's because the equation, the differential equation it gives you, does not contain an x variable. Similarly, if you go from up down and those line segments look exactly the same, that means that the y's don't change the slope, and that is because the differential equation does not contain a y variable. Now if you can identify these, you can match slope fields to differential equations much quicker. And then for the rest that don't have these patterns, all you have to do is go to each line segment and compare it to each x and y coordinate. And if that slope is opposite or different from the x and from what it's supposed to be, you know that's not the slope field that is supposed to match to that differential equation. Now for an example. Now this example is from the apcentral.college board website for slope fields, and it's number 18, and it has five parts: A, B, C, D, E. Now the first one says sketch a slope field of dy dx equals x and y, which is what I have in the green on this graph. The red is for B and D. So in the green, you can see it's just a bunch of line segments here on this graph, and I got those by going to each coordinate and applying it to this differential equation and drawing the slope field that represented that slope at that point. So you can use a chart to sort of visualize it better. And as you can see, I put 0, 0, which is an indeterminate form, and at x and y coordinates 0, 0, I just left it blank, because if it's indeterminate, you can't do anything with it, just leave it on. But if you have a 0, 1, x equals 1 and y equals 0, which is a slope of undefined slope, you can draw an undefined slope, which is just a vertical slope, to represent that undefined slope, which is what I've done for every y equals 0 on this graph. Now, if that's for A. For B, it says sketch the solution curve that passes through 0, 0, 1. So all you have to do is you go to 0, 1, which is this upper function right here. You go to 0, 1, and you connect those line segments, and you're good to go. You just connect them. Like when you were 5, you connect the dots, you connect those line segments. Now for C, which is more of 9.3, but I felt the need to show you particular solutions to explain my reasoning on the importance of slope fields. So C, it says find the particular solution with the initial condition f of 0 equals 1. And what you do is you have dy dx equals x over y. So you separate them, you separate the variables, and you integrate the variables. And you end up getting half y squared equals half x squared plus c. Now c is a constant, so it can change, and all you have to do is just write c. This c over here, this c over here, and the c over here are different, but it's a constant. It's not a variable. It doesn't really matter. You end up getting y equals x, the square root of x squared plus c, and since it gives you 0, 1, you end up getting that c equals 1. And then you find the particular solution, y equals the square root of x squared plus 1. And that is what this function is. Now, why am I showing you something from a different lesson, even though it's a part of a larger problem of the College Board website? I wanted to show you, first of all, that this graph that I got simply by using slope fields is this exact same one that you would get if you had this particular equation from the beginning. Now, if you wanted to, let's say, make a translation, and you only had this graph right here, maybe some people forget let's say if they want to translate it up, some people forget if they had to add 1 to the outside of the square root, or the inside of the square root, or the inside of the x squared. So some people don't know whether or not to put x plus 1 squared plus 1 and square root that whole thing, or x squared plus 2, or x squared plus 1 square root of that whole thing, and then plus 1. So some people just forget, but that slope field makes it real easy for you. All you have to do is go up one and follow those slope lines. Just follow them. Good, and you're good to go. Another reason a slope field is important is because if you have a differential equation and you can't differentiate, so let's say if it's dy dx and some obscene function that you can't differentiate, you can't separate the variables, well, you can still find the graph by simply using a slope field, which is the beauty of a slope field. You don't need the original equation. You don't need a general equation or a particular equation. All you have to do is draw a slope field. Now, it is a hassle sometimes to individually draw those line segments, but hey, you do what you got to do to get the end result. Now, finally, I'd like to talk about Euler's method real quick. And we didn't cover this in class, but it was in the book, so I felt the need to explain it. Now, Euler's method is another type of approximation, similar to that to tangent line approximation. And instead of using a tangent line and just going along the line over and over throughout the whole approximation, you use slopes at differing points to approximate. So what does that mean? I'll show you. This example says, given dy dx equals 2 times x minus 1 and the point 1, 0, right? So you differentiate and you get y equals x minus 1 squared, and they want you to stop at f of 3 equals 4. So this graph in purple was already given to you in the problem. The green is what I have added to it. Now, you see this graph right here. It has dy dx, xy, change in x or dx, dy x plus dx, y plus dy, which are each their coordinates. Now, change in x, which is very important, is the distance from one x coordinate to another x coordinate in which you stop and you change the slope. So you could have 0.1, and every 0.1 you'd have to change the slope, and you'd get a better approximation to the original equation. So basically what you do, you have the original equation in purple, and then you start at 1. Now at 1, when x equals 1, the slope equals 0. So you just draw a slope of 0 from 1 to 1.5. And at 1.5, because the change in x is 0.5, like it says right here, you just go 0.5 and you stop right there. And you find the slope from 0.5 to 2, the next distance. So instead of going along that whole tangent line and crawling, like just having one line all the time at the x-axis, you stop and you change the slope, so you have a closer approximation to the original function. And you just keep going, you go here, you get that slope, which is 0.5, and you go up and you stop at 2, and you change the slope again, and you get a slope of 2, and you go 0.5 again, and that just allows for a closer approximation. So that is all. Have a nice day. Thank you for watching.